So let's first draw what's going on. Before the collision, this object is moving. So here's where the collision happens. Pow. It's moving 60 meters per second to the right at an angle 20 degrees above the horizontal. So before the collision, it's doing this. And then after the collision, and that speed is 60 meters per second. After the collision, it's moving 70 meters per second to the left at an angle 40 degrees below horizontal. So it's going this way, where this angle is 40. That doesn't really look like 40, but okay. And so we know that the impulse over that interval is equal to the momentum at instant 2 minus the momentum at instant 1. So we have to come up with those momentum vectors. And those are equal to the mass times the velocity at instant 2 minus the mass times the velocity at instant 1. At instant 1, the velocity is 60 times cosine of 20 sine of 20. Can someone tell me what those components are? Yep. Okay. Okay. And if you didn't get that, you might have, your calculator might be in radians. That's usually the first place to look if you have, I know in your different classes you're having to, even in this class, you're having to go back and forth between radians and degrees. So be sure you get that right. And then at instant 2, the velocity is 70 times, what's the angle for this one? Negative 140 will work, yep, or positive 220. So what do you get for that? That's just pretty much 45, isn't it? Okay. Those are the velocities. We need the momentums. So the momentum at instant 1 is this times the mass. So the mass is 0.02. So what do you get when you multiply 0.02 times this vector? 1.12. No, 3, 8. Okay. And then what's the second component? 0.410. And that's kilogram meters per second. And then the momentum at instant 2, what do you get for that?
Negative 1.072.
Okay. And the second component?
Negative 0.9.
So the impulse is negative 1.072, negative 0.900, minus 1.128, 0.410. And what do you get for that? Negative 2.200. It's fate. And what do you get for this one? Negative 1.310. Kilogram meters per second. Okay. So now for the impulse part. That's the momentum part in the impulse momentum equation. The definition of impulse is the integral over the whole time interval of the force as a function of time dt. So I'm going to break that up into two separate components. The first one says the integral over the time interval of fx dt and the integral over the interval fy dt. And we're going to assume, I mean, it's not true, but we're going to treat it like fx and fy are constants because we're just trying to find the average force. And so this is equal to the integral from 0 to 0.005 of, we can pull this out because it's constant, dt, and we get 0.005 fx. And this one we can write as the constant fy times the integral from 0 to 0.005 dt is equal to 0.005 fy. And so now we get two equations for the force momentum equation. The first one says 0.005 fx is equal to negative 2.20. And so what do you get for fx?
Negative 440.02.
440 point what?
02.
02. And that's newtons. And the second equation says 0.005 fy is equal to negative 1.31. So what do you get for fy?
Negative 262.07.
And so all that together says that that average force is equal to negative 440.02, negative 262.07, and those are in newtons. And you know, we're always assuming that that the form of this force function as a function of time is constant. It's because we don't have any more information, and that's a simple way to approach it. If we wanted, we could assume that it's a parabolic shape, a triangular shape. We have all these options, and then we just fit the curve. You know, we do that integral and match the coefficients to the forces. So we could do that. But the only problems we're going to do, we're going to assume that that's constant. Yep.
When you were calculating the impulse, why did you use the speed?
To calculate the velocity, it was the speed times the direction. So the cosine and sine give you the direction multiplied by the speed, and that gives you the force vector. Yep. So you need to get the velocity vector, and if you're given a speed and a direction, you need to come up with the components from that. Any questions about that one? Okay. So go ahead and do number 4. So for this one, we have a 10 kilogram mass that bounces on the floor. It comes in like this and leaves like this. Before the collision, it has a speed of 10 meters per second. And after the collision, it has a speed of 8 meters per second. And we want to figure out, first, what's the average net force during the collision acting on that mass. Okay, so the first thing we have to do is figure out the change in momentum. Because the impulse is going to be equal to the change in momentum. At instant 1, the velocity vector is 10 meters per second times, what's the angle I need to use there? Negative 80 will work, yeah, or positive 280. So what do you get for that? Whoa, that was weird. Okay, so what do you get? 9, 8. I think that should be positive 1.74. Is that right? And then negative 9.85. Is that right? And that's meters per second. And so the momentum, this thing has a mass of 10 kilograms. So the momentum is the mass times velocity. So 17.4 negative 98.5 kilogram meters per second. And then at instant 2, we have the speed, 8 meters per second, times what's the angle representing this one? Yes, right, 78. So cosine of positive 78 degrees, sine of 78 degrees. And so what do you get for those components?
1.66.
Okay. And so you get a momentum that's equal to 10 times this, so positive 16.6, positive 78.3. So now the definition of impulse is the integral of the force as a function of time with respect to time. So we can break that up into fx times the integral from 0 to, what was it, 0.03 dt. And so that's 0.03 fx, which is the way it always works. When you take the AP test, write that integral in there, okay? So they know what you're doing. And then for the y component, fy times the integral from 0 to 0.03 dt. So 0.03 fy. And now we can use the impulse momentum equation. So the first equation says 0.03 fx is equal to 16.6 minus 17.4. So what do you get for fx? Okay. And seems in the right ballpark.
Well, what do I do it here? Negative 0.8, because that's negative 0.8, right?
Negative 0.8 divided by 0.03.
Yeah, I get 26.6 repeated.
Okay. And then for the second one, we get 0.03 times fy is equal to 78.3 minus 78.3 minus negative 98.5. And so what do you get for fy? 589, like this. Ooh, that's big. It's a heavy mass. And so the average net force is equal to negative 26.6, 5893.3 newtons. Okay, so now this is a longer impact, so let's figure out how much the weight factors into this. So for part B, we want to figure out what's the average impact force on the mass. So we have, if we think of a free body diagram, we have this unknown force vector. We don't know anything about it, that's coming from the ground. And then we also have a weight force that's equal to 98.1. So Newton's second law says 0, negative 98.1 plus F impact X and Y components is equal to the net force. So negative 26.6, 5893.3. And so that average impact force is equal to negative 26.6 repeating. And then what do you get for the Y component? positive 5, 9.
5991.
And then 3's repeating. Yeah. Okay. Okay, so here's sort of an intuitive question. Thinking about this impulse-momentum relationship. Think about, so if you had to jump off the top of a short building, think about what you would rather land on. Okay, are you ready to concentrate? Would you rather land on concrete or on a pole vault pit? Concrete? Okay, yeah, it was mixed reactions. That's a tough one. What? No, you're pushed by the mafia. Okay, so why is that in terms of the impulse momentum equation? Why are you better off landing on a pole vault mat, thick pole vault mat? Say that it's flush with the ground, though, so you don't get any advantage from falling less far. Why are you better off landing on a pole vault mat versus landing on the concrete? Yep.
It obviously compresses. I'm not sure how that affects physics.
Okay, well, think about how it affects this equation.
It takes a longer time, so there's a lower force because it's spread out.
That's right. So your momentum is the same when you hit the mat and once you come to rest in either case, right? So the change in momentum is the same in either case. The difference is that the duration of that impact is drastically longer with the pole vault pit. And so in this step where, if you think about this calculation we did, in this step where you're dividing the change in momentum by the duration, you end up getting a drastically reduced average force, which is what you want. You want a reduced average force acting on your brittle bones. It also, so the pole vault pit also spreads out the surface area of the impact a little bit, a lot, which helps you a lot. But you can imagine, so imagine if someone knew exactly how you were going to fall and out of concrete molded it exactly to your body, so you didn't get any advantage from the mat of spreading out the surface area. Like you land on concrete that spreads it out perfectly, you'd still think like, no, I'd still prefer not, you know, right? Yeah, that still doesn't sound so great. But the really big advantage is that the pole vault pit causes this big increase in the duration of the impulse. And so it decreases the average force. Okay. So let's skip to number 6. So you can think of this as these two objects held together by a coiled spring, and there's like a latch holding that spring compressed. And at a certain instant, that latch comes undone, and whatever these internal loads are allowed to free up. This explosion happens, moving these two objects apart. Okay, so see if you can make sense out of that. So the idea here is conservation of linear momentum. So before the collision, so total linear momentum before is equal to the total linear momentum after. So before the collision, you have a 5 and a 3 moving as a single object with a velocity of 6.4. And after, you have a 5 with a new velocity of 15, -8. And a 3 with an unknown velocity vector. So can you solve this?
Yes.
How do you know? Well, because you already did it. But if you hadn't already done it.
There's one independent variable that keeps the two equations
That's right. So it's a system of two equations for two variables. So you get 48, 32 is equal to, what's that? 75, negative 40, plus 3vx, 3vy. Okay, so what do you get for vx? And what do you get for vy? Positive 24. Okay. Any questions about that one? Okay, one more to go. Number 7. Okay, so the first part, if it's inelastic, that's sort of the good news. That's the news you want to hear because that's a lot less time consuming. So we have, before the collision, we have a mass of 0.2, and it's moving at, let's think of this one as on the left, so it's moving at 4.50. And then the one on the right is moving to the left. That has a mass of 0.6, and its velocity is that. Any questions about coming up with those velocities? You could switch those signs, but they have to be opposite because they're moving towards each other. And then after the collision, you have a combined mass times the velocity vector. And so 0.9 minus 1.2 is equal to 0.8 Vx. So Vx is equal to, what's that, negative 3/8?
Where do you get the negative 2 from? It says no, that it's negative.
It says that they are rolling towards each other. So one has to be going in the opposite direction of the other one. So you could do this problem with either one going positive and either one going negative, but their signs have to be opposite. And then Vy is equal to 0. So after the collision, you have this. And if you switch the signs, you'd get positive 3/8. Okay, now the elastic one. This one's a nuisance. So we're going to use the x component, the component in the direction of the motion, for the first equation. So before the collision, we have 0.2 times 4.5 and 0.6 times negative 2. And after, we have 0.2 times, I'll call it V1, plus 0.6 times V2. And I'll rewrite this as 0.2 V1 plus 0.6 V2 is equal to negative 0.3. And actually, since we're going to have to do a substitution, let's just set up the substitution, divide everything by 0.2, And then you get V1 is equal to negative 3V2 minus 1.5, right? And then to streamline everything one more time, let's write this out. We know we're going to have to substitute a squared value into the elastic equation. So this is equal to V1 squared is equal to negative 3V2 minus 1.5 squared. That's the same thing as 3V2 plus 1.5 squared. And so you get 9V2 squared plus 3V2 plus 2.25. And now that's the relationship that we're going to substitute into the elastic equation. You can do this stuff in any order, obviously, but so now we have to use the fact that the kinetic energy is conserved. So we have 1/2 times 0.2 times 4. What? 3. Oh, I keep doing that. I did that last time too. Thank you. Yeah. Okay, so the kinetic energy equation says 1/2 times the mass of the first one times its speed plus 1/2 times the mass of the second one times its speed, P4, is equal to 1/2 times the mass of the first one times its speed squared after, plus 1/2 times the mass of the second one times its speed after. We'll cancel all the halves, divide everything by 0.2, and we get, what's 4.5 squared? So 20.25 plus, I think this is, what? No, because I divided everything by 0.2. I'm sort of skipping steps here. So, so this will be 12. This will be V1 squared. And this will be 3V2 squared. And then we can substitute this in for that. And we get 32.25 is equal to 9V2 squared plus 9V2 plus 2.25 plus 3V2 squared. So you get 12V2 squared plus 9V2 plus 2.25. Solve for V2. You can use the quadratic formula. So 12V2 squared plus 9V2 minus 30 is equal to 0. Can someone solve that quadratic formula? Okay, so there's a -2 and a positive 5/4. Okay, so that's two solutions. We want one, so which one do we accept and which one do we reject and why? One of them is the old one. That's exactly right. So this is what mass 2 was doing before the collision, so we don't care about that. We want this one. So V2 after the collision is equal to 5/4, so 1.25 meters per second. V1 you can get by substituting back into this equation. So what do you get substituting here?
It should be negative 5.25.
Negative 5.25? Negative 5.25. And then if you want these as velocities, V2 is equal to 1.25, 0. V1 is equal to negative 5.25, 0. By the way, there's we're always doing these with the direction of motion being along a line, and then the motion after the collision being along that same line, like objects hitting squarely into each other. You know from playing pool that that doesn't have to be the case. But to solve those kind of problems, you'd have to specify like an angle that one of them goes at. So we're not doing problems like that, but it's not too hard to figure out how to do it. Yep.
I have a question. So up there you have both the velocities are positive. Did you say one of them has to be negative?
Up where?
The kinetic energy.
Yes. So this is negative, but you square it.
Okay.
So it just comes out positive.
Oh. Okay.
Yep. Any other questions? Okay. So remember, the test is on Tuesday, so plan accordingly.